This is a polyprotic acid. So the first thing we recognize here is that that bicarb anion that's produced is going to dissociate by releasing that second hydrogen in a reaction with water to form the carbonate anion and another H3O+. So let's do that calculation with our Rice table. We know that the initial concentration of the bicarb anion is 1.5 times 10 to the minus 4 molar. We just solved for that from the first dissociation. Our initial condition before any reaction takes place is that we have 0 carbonate anion in solution, and the change in this bicarb concentration is minus X, and that's going to produce an equal amount on the right-hand side, so that at equilibrium we have 0.00015 minus X. And that produces, again, at equilibrium, a concentration in the carbonate anion of X. So at equilibrium, we have the fact that the H3O+ times the carbonate anion divided by the bicarb concentration is equal to the first acid dissociation constant. But we know something else, and that is that this reaction is such that the concentration of the H3O+ cation is identically equal to the concentration of the bicarb anion. And that means that we can cancel the H3O+ and our HCO3-, and that means that the carbonate anion is identically equal to the second acid dissociation constant, and that is equal to 4.7 times 10 to the minus 11. Now that's very important because that's some 4 orders of magnitude smaller than the first acid dissociation constant. So we can calculate at equilibrium each one of the species in this mix, and that comparison is what we're looking for. So we know that our H2CO3, the concentration of our carbonic acid, is identically equal to 0.05 molar. And the concentration of the bicarb anion, we solve for that, that is equal to 0.00015, or 1.5 10 to the minus 4 molar. But now we're ready to add the concentration of our carbonate anion that we've just calculated. And that concentration, interestingly, is equal to 4.7 times 10 to the minus 11 molar. So we can calculate the pH immediately. That's equal to minus log to the base 10 of H3O+, and that is equal to 3.82. Look what's happened. We started out with 0.05 molar of carbonic acid. The first dissociation constant gave us a concentration of the bicarb anion of 1.5 10 to the minus 4, and the dissociation of that bicarb producing the carbonate anion gave us a carbonate anion concentration of 4.7 10 to the minus 11 molar. A massive decrease in concentration between that bicarb and the carbonate anion, and the reason for that is reflected directly in the acid dissociation constant. And that's what polyprotic acids do. They will give up their first hydrogen with a reasonable acid equilibrium constant, but the second hydrogen atom is very difficult to remove from the molecule, and that produces a very small equilibrium constant and a very low concentration of that second product coming out of the dissociation of the polyprotic acid.